There are also special rules for certain types of summations. We need to know in case we need to make some more difficult computations. So for instance, one of them has already been mentioned, sum I equals 1 to n, where you see nothing inside the sigma symbol. So that means it's really an invisible 1 there, and this is just saying 1 plus 1 plus 1 n times. There'd be n terms, and they're all the number 1. So you're adding them together, so of course you must get the number n. Okay, so any expression like this, where this is the end of the index of summation, you're going to get n for your answer. More complicated, though, and more necessary for these types of problems is when you want to add up something like this, right? Which really means 1 plus, and I is going to change to 2, and plus I is going to change to 3, I is going to change to 4, and so forth. This is just adding up the first in whole numbers, right? First in positive integers. So plus, and then dot, 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 until where? Until n minus 1. Eventually you get to n itself, right? So maybe I'm adding up the first 100 integers, the first 1,000 positive integers, whatever it is, right? But it's a lot. So therefore, if we had a formula for some kind of expression like this, it would be much better than adding directly. It would take too much time and computational energy. So it turns out there is a nice formula, and it is a simple multiply and divide, which I do in the reverse order. I divide and multiply. Okay, so n plus 1 and 2 is the formula that describes this particular summation. So let's imagine for a second you have to add up the sum of the first 100 natural numbers. All right, so from 1 to 100, you got to add them all together. So that's the same as taking 100 times 101 and dividing by 2. And since these are always consecutive integers here, one of the two has to be even, so you can divide it off first. So for instance, in this computation, if I wanted to find, all right, find the sum 1 to 100, right? Which in this case, right, would be 1 plus 2 plus 3 all the way to 100, right? Adding all of those up together. We could waste no time and simply do 100 times 101 on 2, but since one of the two will be even, I can immediately divide by the 2 down there and get a 50 in this case. 50 times 101 is, of course, 50/50. So 5,050 is the sum of the first 100 natural numbers. So that's a much more efficient way to compute that than to actually go through and add them all up in the most direct way possible. All right, so sometimes it's not just I to the first power. Sometimes you want to find some of the first in squares, right, or cubes. So each one has its own formula. There's actually a formula for all powers that you would want to add together, but they get very cumbersome. So these are the ones we'll deal with the most. So 1 squared plus 2 squared is what this is saying, plus 3 squared. This is going to be, it's going to get large fast because you're squaring all the numbers now. And then eventually you'll get down to n squared, right? Okay, so it turns out there's a formula for this as well. It is n plus 1, 2n plus 1 over 6. Okay, so that will come in handy, and then the one for cubes also comes in handy over the next few sections. So equals 1 to n of I cubed, some of the first n cubes. Also will get large very quickly, because now you're cubing all of these integers. Eventually you'll add the nth cube. Okay. And strangely enough, this formula is exactly the square of the first one we illustrated here. Plus 1 on 2 quantity squared. Okay, so there's our formulas, right? There. That is that. And that one is that one. There are formulas that we'll need to employ in these sections. I'll now try particular example from the textbook to illustrate this.